So in my last talk of the day, I will talk about seismic site response simplified methods. Before you do a more sophisticated analysis, you need to know what the answer is before you do the calculation. The more sophisticated the analysis, the more likely a mistake will be made. So I always say never perform a calculation unless you already know what the answer is. The purpose of the calculation is not to discover something brand new, it's to see nuances and gain insight and to be able to refine your estimate of the answer, not discover it. I want to emphasize two things in this chart that you've seen a few times. I keep on bringing this up because I was a structural engineer and I still interact with some structural engineers that go, soil is not that important. It's all about the moment-resistant frame, the shear walls, it's all about inter-story drift, it's about beam column connections, and I'm not saying that that stuff is not important. But then I ask them, if you don't want to invest in discovering how deep your soil profile is, let me ask you a question. The meanest lawyer in Colombia is going to build a penthouse on top of a building. And you have to design that penthouse. Do you care how tall the building is? You go, of course I do. You care whether it's a 1-story building, a 10-story building, or a 50-story building. Do you care about the stiffness of that building? Whether it's a shear wall building or a moment-resistant steel frame. The structural engineer says, of course, I can't build the penthouse on the top floor of a building unless I understand the building. I go, then I agree. You can't build a building on top of a soil deposit, which is a soil structure, without knowing its stiffness, its depth. All those things are important. When you build a structure, you are building it on a soil structure, and you need to know its dynamic response characteristics. And one of the most important things is its fundamental period. One other point I want to make. 4 times the thickness, that's the soil depth, or the depth to a significant impedance contrast, the shear wave velocity is the average shear wave velocity of that soil deposit. The way to calculate that is to take the summation of each layer's thickness times the shear wave velocity of each layer and divide it by the total thickness. Do not use the formula that's used to calculate VS30. That method of taking the distance over time, where you use the reciprocal in the denominator, is biased and wrong. When we brought this up to the people calculating VS30 that way, they said, oh, well, we deliberately did that to overestimate the shear wave velocity to be conservative. But it's not always conservative to use site class E instead of site class D in the short period range. So actually, that's not true. Ricardo Dobry did an extensive study of 7 different ways of estimating site period, and this is the best way of calculating. This is the way Shake calculates it. It's do not do the code-based method. Site amplification is seen very clearly here for a equivalent linear analysis, where you have a little bit more than, you have 40 feet, and you have a shear wave velocity that's defined, and you have a level of damping of 10%. Using the fundamental frequency is Vs over 4H. This has a fundamental frequency of 2.5 hertz. Site B is the same height or thickness, but the shear wave velocity is different, so its natural frequency is 10 hertz. You can clearly see the difference in site A amplification versus site B amplification. So if you're building a building at this site, you care whether you're on the peak of the spectra or not. The site A also shows the second mode and third mode There are sometimes the second mode is somewhat important. There's very few times where the third mode is important. What's most important is the first mode response. I spent my initial part of my academic career in Indiana, where you do not have soft clays like you have here or we have in the Bay Area. And so I focused on deep, stiff soil sites. And this is looking at the ratio of the calculated acceleration response spectral values across different periods of soil versus outcropping rock. So I took an outcropping rock motion, deconvolved it down with shake, and then propagated it up and looked at the soil spectra versus the rock spectra. This is for a magnitude 8 earthquake with a PGA of 0.3. And what you see is depth matters, because for a stiff soil deposit, as you increase the depth from 30 meters to 60 meters to 150 meters to 300 meters, you are changing the site period. And you can see how the site period amplification increases in terms of its period. Because the deeper deposit, the waves have to go through a deeper deposit, the amount of amplification is less. But if you are a tall building, you do care beyond 30 meters. It was an oversimplification, in my view, to put everything on VS30. The upper part of the soil profile is not the only part that matters. Deep, stiff soils matter, so depth matters. Now, if you put a soft clay on top of a deep, stiff soil deposit, and you do the same experiment where you just increase the depth beyond 30 meters, then the soft clay is like a filter on top of a filter, and that filter of the soft clay is most important. So when you do have soft clays, it is important to focus on the properties, the stiffness and depth or thickness of the soft clay. So soft soils are important. So when I look at doing a site response analysis, whether sophisticated or simple, at a minimum, a valid site response method has to capture 4 things. It has to acknowledge geology. We know there's differences between rock and soil. You have to at least look at a geologic map and treat those 2 materials differently. But the more we look at it, not all rock is the same, and not all soil is the same. So you should go from hard rock to soft rock. You should distinguish between hard rock, medium stiff rock, and soft rock. In fact, soft rock might be very similar to a very stiff cemented soil. Then soil can go from very stiff cemented soils to very stiff, to medium stiff, to soft. So the method should differentiate between those different stiffnesses. Depth to bedrock is important, as shown earlier. And depth to bedrock is really the depth to the significant impedance ratio, where the material below that impedance ratio is rock-like. The impedance ratio for waves going up through rock into soil is the mass density of the soil times the shear wave velocity of the soil divided by the mass density of the rock and the shear wave velocity of the rock. These will vary a bit, but what's most important is the shear wave velocities. If you get contrasts of a factor of 2 or so, those are ones that are important, where the shear wave velocity, where the impedance ratio is maybe less than 0.5. And then we know that soil response is nonlinear. There has to be a recognition that how a soil responds under low level of shaking of, let's say, 0.05 G is very different than when you have 5 G of shaking. And so it has to capture that variation of material stiffness and damping with increasing shear strength or level of shaking. There are 5 general procedures. This is the order in which I typically do the analysis. I start with empirical ground motion models because they're easy. You have a spreadsheet, where given a magnitude, distance, and site class, you can estimate what the 5% damp pseudo-acceleration spectrum will look like. There's also ones that give you the estimate of the peak ground velocity. Then I move into what I call simplified geotechnical methods. The newest and most robust is probably that by Sayan and Stewart. It's both has an empirical basis, but it's been supplemented by a lot of nonlinear calculations. Walling et al. Have another method, and I still like the Raymond Seed et al. 1997 method for seeing things, and we'll show that. Then, of course, you have to do it by the code. I'm just going to talk a little bit about the ASCE 716, which actually is not the code we use in the US right now. We still use ASCE 710. So I always remind people, if you do things according to the code, you're at least 10 years out of date. Sometimes 20 years, because ASCE 710, which we're using in the US now, was really published in 2010. It's based on research that they knew about in 2005 and voted on. It's at least 15 years old. And then equivalent linear analysis, which more commonly now is done with deep soil, and then the fully nonlinear analysis, both 1D, 2D, 3D. If we look at the site response as shown in the empirical ground motions, as I mentioned, it's primarily a long period effect. Sites affect tall buildings. They affect short buildings, but they affect tall buildings in a more pronounced way. This formula is used for BS30 because that's what they decided to do, but that's not the formula you use to estimate the average BS. You cannot use these for low stiffnesses. Realize that they recognized that BS30 was weak and incomplete, so they started to add the depth to a shear rate velocity of 1 kilometer per second material, and they then added 2.5, the depth down to 2.5 kilometer per second material. That's an effort to try to pull in depth. It's still incomplete, but it's better than just using BS30. Sometimes it's difficult to estimate Z1.0, so I have some correlations. If your BS30 is, let's say, 360 meters per second, then on average, the depth to 1 kilometer per second material will be 0.4 kilometers. If your Z1.0 is 0.4 kilometers, then your Z2.5 might be close to 1.4 kilometers. The spreadsheet that you have also provides some generic estimates. It's always better to use measurements at your site and better site-specific geology to make more informed estimates. Of the geotechnical methods, this is the method that Professor Kramer talked about. I just want to remind you that these papers and spreadsheets are available for estimating the period-dependent amplification. As you can see, there's a kind of a short period and long period amplification, and they depend on the site, whether it's a soft site, medium stiff site, or rock site. Rock sites tend to be linear, so you basically, whether it's short period or long period, you essentially get the same value. Whereas when you get to really soft soils, you'll see a difference between amplification in the acceleration range, around 0.2 seconds, and amplification in the velocity range, maybe at around 1 second. You'll tend to have more nonlinearity at the PGA or the spectral acceleration at 0.2 seconds, and less nonlinearity at the greater periods. I like this simplified geotechnical site response, and I'm showing you this graph because it's not that simple, but it is as simple as it can be. That's what you want. You want a method that's no more complicated than it needs to be. And this is as simple as we can make it. When you look at these type of things, I regret, because I'm one of the co-authors, of not flipping them around, because I think you should always read these charts from the bottom up. the most important thing is, do you have deep, soft clays? Do you have liquefiable material? Because that changes everything. Then do you have soft clays of normal thicknesses? Then do you have deep, stiff soils, shallow soils, rock, or hard rock? So let's walk through those. If you have highly organic or deep, thick, soft clays, peaty organic materials, or you have sites that might undergo ground failure, nobody should be giving you a simplified method because those are complicated phenomena. If you have a soft clay site, you shouldn't just treat all soft clay sites the same because we know intensity of the ground motion matters. So notice how this method breaks site response for soft clays into different categories, whether the bedrock acceleration is low, less than 0.25 G, whether it's intermediate, or whether it's high. It also brings in the fact that soft clay from 10 to 100 feet is one category, but if you have soft clay that's more than 30 meters, that's an entirely different phenomenon, and you should treat that differently. Same thing with high PI or high plasticity materials. In fact, a lot of your sites might be actually E3 or E1 in Bogota in the northern part. Then for stiff soils, if you don't have liquefiable, highly organic materials and you don't have soft clay, then you look at whether you have soil. And I like this because it differentiates cases where the depth of soil is less than 200 feet for a cohesive material, or it's greater than 200 feet. We know from those calculations I showed you, and we know from empirical evidence, that the depth of the soil deposit matters. And it matters whether the depth is less than 60 meters or greater than 60 meters. I would like to take some credit for this, but the late Professor Harry Seed, when he first did this work, differentiated between shallow stiff soil sites and deep stiff soil sites. Why we forgot that lesson, I don't know. And then there's a difference between primarily sandy sites and clayey sites. And then rock. Not all rock's the same. You can have very hard rock with very high shear wave velocities greater than 1,500 meters per second. You can have less hard but still competent rock. But one of the more dangerous materials is actually soft weathered rock on top of hard rock, or cemented stiff soils on top of hard rock. You get the impedance contrast to amplify the shaking, but the soils are so strong you don't get as much nonlinearity, so you get amplification across a larger range of accelerations. I like looking at what's called a bend-over curve. So this is the peak ground acceleration of soil versus the peak ground acceleration at rock. And so this method says, if I'm a D site, this is my bend-over curve. I will get amplification at low accelerations, but I will get de-amplification, one-to-one lines right there. So if 0.7 G at this D site, I'll actually only get 0.5 G out of the top. If I have 0.05 G, I'll get 0.15 G out. So you're seeing the fact that at soft soil sites, you get amplification at low intensities, you get de-amplification at high intensities. The other reason I like this is sometimes people do a calculation and they put in 0.7 G and they get 0.2. And I go, run the ground motion at 0.05. And if at 0.05 they get this, they have a bend over curve that looks like this. Most of the time they made a mistake, or they have a model that's over damping and failing, and they're getting attenuation all the time. So it's a good sanity check. Then kind of following this format, if you already have the peak ground acceleration, now we want to look at spectral shape. So we'll look at the response spectra at every period, the response spectral value at every period divided by the PGA. So these are normalized to 1, so you can look at the difference between rock, stiff soil, deep stiff soil, and softer soils. And even with site class E, for very soft soils, we're drawing them with dotted lines because we realize we don't have much empirical evidence and we have uncertainty in our calculations. These were drawn conservatively. The norm now is to use median ground motions given a hazard level. So divide all the spectral values here by 1.2 to get the median estimates. So this is the methodology of Seed et al. 1997, which, to be fair, is actually Seed and Idris, the late Professor Harry Seed and Idris, 1982. It's the same methodology, it's just been updated with new calculations and refinements. But you estimate what would be the PGA rock, you classify your site, start from the bottom up, you then use the bend-over curve, given the site class, and the PGA of rock to estimate the PGA of your site. You select your site-dependent normalized spectra, and then you multiply those two together to get your response spectrum. The third simplified alternative is to use something based on the code. And I'm looking forward to ASC 716 because it gives us an idea of where the profession is going, at least in the United States of America. It still has a two-part system. It has a spectral design in the short period range, or spectral design value in the short period range, and then it has anchor point on what is largely the value divided by t, so where the spectral acceleration is largely a function of 1 over t in the longer period range. At very long periods, there's an adjustment that's shown here, but let's just focus on this for now. But as this goes up or down, it will just change this intersection point. So what's really important here is TS, is the value of SDI divided by SDS, which sets this point. So this is controlled in the short period range, and this is the relationship of how it falls away, 1 over t. The nice thing is with 2 parameters, the old code only had 1. But it's important that now we have 2 parameters. We look at this short period side and the long period part of the spectrum because they're different, and we adjust them based on site class and also the intensity of the motion. ASC 716, even though it's supposed to be forward-looking, still allow engineers to estimate properties in the upper 30 meters with standard penetration and undrained shear strength. No. In today's world, if someone's going to do a site response analysis or evaluate the ground shaking that may affect a structure, it's not expensive to measure shear wave velocities. Measure the shear wave velocities and at least classify your site based on the shear wave velocities. Then there is the short period amplification factor, which is obviously a function of the site class, but also the intensity of the rock motion. And there's a long period. That's what's multiplied to get the spectral acceleration at 1 second. That one is a function of site class and also a function of intensity of the ground motion. As the ground motion becomes more intense, you see how the amplification factor decreases. What's interesting here is the code says, the modern code going forward says, don't ask us to give you a simplified method if it's site class F. That's smart. Don't ask us to estimate the long period part for site class E, a soft clay site, because you should do site-specific analysis. In fact, if you refuse to do site-specific analysis for soft clay sites in the short period area, we're going to penalize you. We're going to use the numbers from site class C, and that's the way it should be. If you do something that's overly simplified, you should be penalized. When you do things with a more sophisticated model and get closer to the truth and reduce the uncertainty, you should get the benefit of having lower accelerations if that's what it's going to be. They did the same compromise in Site Class D. Codes are always debates. It's like making a new Declaration of Independence or new bylaws to our committee or whatever. So the structural engineers, at least in the United States, go, well, we don't want to waste money on new geotech, so we'll give structural engineers exceptions. Okay, Site Class F. Yeah, we know it's going to liquefy, it's going to do all these interesting things, but a lot of our buildings are short period buildings, so we'll let you get away with not doing a site response analysis. That's not always the right thing to do, and Professor Kramer will point that out. For Site Class E, you should do a site response analysis. It says that, but then it gives you this exception. Okay, you should do this. Okay, I'll give you an exception. If your building period is less than TS, that number that I showed you was calculated, then you can use the FA for Site Class C, because we're penalizing you. The same thing for Site Class D. If your T is less than 1.5 TS, we'll have you use an amplified velocity factor to penalize you if you want to keep things simple. The trend is toward site-specific analysis. It's 2019. SHAPE was invented in 1972. It's time for us to go beyond the overly simplistic and use our tools to gain insight and refine our calculations and offer our clients a better service. ASC 716 provides guidance on selecting ground motions. And I think very importantly, as much as I believe in site response analysis, most codes have a floor. They go, I don't want someone to overdam, do a ridiculously bad analysis, and end up with ground motions that are way below what they should be. So while I trust engineers to always do the right thing, I believe that humans are inherently good, not evil. Other code writers write it the opposite way. They believe that you are evil, and you're going to do everything in your power to do things wrong to save money. I believe engineers, especially civil engineers, are the most noble of people I've ever met. If I was to be stuck on an island, I'd rather be with civil engineers than a bunch of lawyers. That's actually not a compliment, because anyone would rather be with anyone than lawyers. But I'd actually rather be with you than just about any other profession. Maybe I'd want a doctor. So maybe I'd pick a medical doctor, then a civil engineer. I would throw the lawyers into the sea and let the sharks have them. But here's the floor, is whatever you do, you can't go below 80% of the code. This is the methodology, and again, this is not your code, so I don't want to go through the details. I don't want to teach you this. I just want you to realize that this is a methodology that brings in both the short period ground motion and the long period ground motion, the short period amplification and the long period amplification, with an idea that it's a lot more sophisticated than it was 20 years ago, but it's not as sophisticated as it should be. One mistake we have made that you shall not make, and I don't think you've made this, for some reason they decided to not design for the 475-year level, which is 10% in 50 years. They decided to design for 2% in 50 years. And then after doing all of these calculations, you take a magical 2/3 to get you back down to 475. There's reasons for doing this that are political. I don't want to talk about them. What I do want to talk about is soil mechanics. This idea of using really intense ground motions and amplification based on that to come up with your intense spectral accelerations and then taking 2/3 of them would only work if soil response was linear. It's not. It is ridiculous to use a method that's based on linear soil response when we know soil response is not linear. We're fighting to change that. But the code can be used to develop a simplified estimate of a 5% damp elastic spectrum. there are factors and importance numbers. You put all that stuff to one, and what you end up with a site-dependent, code-based design spectrum that you can use to compare with what you got from CEDAW 1997, as well as what you get from the GMM, as well as what you might get from site response analysis. So simplified seismic site response analysis are, first, start with empirical ground motions, but realize they've taken all the sites with VS30 between 180 meters per second and 360 meters per second, and they've put them all together. They've averaged out the personalities of everybody. It'd be like me taking your average dimensions and making a suit for you. Maybe one or two of you might fit into this suit. I wouldn't, because I know I'm beyond the standard deviation of the normal waist, okay? When you're building a site, that site has a personality, that structure has a personality. You want to capture that. The simplified geotechnical site procedures do a better job. We have to do it by the code, regardless of how well it does it. So we look at those three before we go into the site response analysis. Thank you.